In this part of Chapter 4, we look at clocking on the Msp430. We start with, what do you need? What type of clocks do you need in your system? Second of all, what are the 3 internal clocks of the Msp430? We see them listed here. We'll examine each of them. Next, we look at the sources for those internal clocks, the different oscillators, either internal or external. And finally, we look at some of the clock details, device family by device family. So what are your clock needs for your system? Do you need fast clocks for things like communications and high-speed processing? Do you need low power because you're running off of a battery and you want it to go for a long time? How about accuracy? Is that really important? Or are you just doing something very infrequently and the timing isn't really all that important? Maybe power would be more important. How about fail-safe? What happens if you use a crystal on the board and it fails? And I'm guessing we all want inexpensive. Most of us will need a combination of these different clock features. As you can see, the Msp430 has lots of clock options. What's nice about this diagram is it gives us a good overview of the Msp430 clocking. On the left-hand side, you can see the different oscillator sources. These are the things that generate the clocks. Some of them are internal, for example, the VLO and the DCO. We'll talk more about what those terms are in a minute. Other sources might be crystals or other clock signals coming from off-chip. These then get routed internally through selectors and dividers to the 3 clocks that are found inside all of the Msp430s. Looking at these 3 internal clocks, starting from the bottom, let's look at M clock, or the master clock. This is primarily used to drive the CPU. The other 2 clocks, SM clock and A clock, are 2 different clock options that we can use for our peripherals. The SM clock is generally used as a high-speed clock for peripherals, while A clock is generally used as a low-speed clock for peripherals. That way, for each peripheral, you have a choice of running it at a higher speed or a lower speed. The advantages of lower speed being lower power, and I'm guessing you understand the advantages of higher speed. As we go through this section, we're going to look at the different clocks, oscillators, and touch on the selectors and dividers as well. This is just one example. Some devices let every clock oscillator go to every single internal clock, A clock, SM clock, or M clock, while other devices aren't quite so orthogonal. We'll summarize that in some tables as we go through this chapter. Let's look at the different internal clocks of the Msp430. This slide reviews what we were talking about earlier. You can see M clock, the master clock, is used by the CPU. SM clock, the submaster clock, is used by the peripherals and is usually set at a fast speed. A clock, the auxiliary clock, is also used by the peripherals and usually set at a slow speed. As you can see in the diagram below, A clock and SM clock are routed to all of the different peripherals on the device. Again, how they get routed is specific to each different device, although you should always look at the options that are available on each specific device's datasheet. But this hopefully gives us a view that, for the different peripherals, we can determine if we want to run them at a higher speed or a lower speed. That's generally how we use M clock, SM clock, and A clock. Next, let's look at the clock oscillator sources for the Msp430. This slide shows us a typical selection of clock sources for the Msp430. Be aware, not all devices have all clock oscillator sources shown here, so you should always double check with the datasheet. Let's briefly look at each of these, starting with VLO at the top of the slide. VLO stands for very low frequency oscillator. It's inexpensive because it's built into the device and it's very low power, but it trades off with that by being slower in the 10 to 12 kilohertz range, and it's not the most accurate clock on the Msp430. The next option found on some of our devices is the reference oscillator, and this runs at a very standard 32 kilohertz rate. It's another example of an on-chip oscillator. The next 2 we show here, XT1 and XT2, represent the off-chip oscillators. Usually those are tied to crystals, but they could also be tied to external clock oscillator that you might have on your board. Usually XT1 is used for either low frequency or high frequency, and XT2 is primarily used for high frequencies. Not all chips have both of them. If you have both, then you'll usually use XT1 for your low frequencies and XT2 for your high frequencies. DCO is oftentimes thought of as the workhorse of the Msp430 oscillators. It's a high-speed internal oscillator. It also wakes up quickly from sleep. It's really an ideal oscillator for using for the CPU, or maybe also fast peripherals. The last one we show here is called mod-osc, or module oscillator. It runs in the 5 megahertz range on most devices, and is usually used to clock the A to D converter and maybe also the flash logic on a device. As you can see in this diagram, all of the oscillators are routed to all of the different internal clocks. And on some of our devices that's the case. But that's not the case on all of the devices. But once again, we ask you to look at your data sheet to verify your device clocking options. This slide shows us those same typical clock oscillator sources and which different devices they show up on. Once again, we're using 3 Msp430 devices to represent some of the differences found across the various Msp430 device families. The G2553 value line device, and you can see that it has the VLO, but it doesn't have the on-chip reference oscillator, REF-O, and it also doesn't have the second external oscillator source. The F5529 USB device has all of these different clock options. And the FR5969 FRAM based device also has most of the clock options. The only one it doesn't have is the reference oscillator. Looking specifically at the Msp430 F5529, we've tried to add a few details regarding the precision as well as the current usage and startup time. I won't bore you by reading the details off of this slide. You can look at the overview shown here or go to the datasheet for your specific processor and look at the specific details on precision, current, and startup times. Let's look at some of the clock details by device family. As shown here, there are at least 6 different generations of MSP4 clock systems. In general, they share quite a few things in common. The whole concept of M clock, SM clock, A clock, and the different clock sources are quite common to these different clock modules. In time, we've added additional features to the clock modules, and hence we've changed the name. In this section, we mostly look at the BCS Plus, the Basic Clock System Plus that's on the value line devices, UCS, the Unified Clock System that's on our F5529 example device, as well as CS, which is the clock system on the FR5969. Jumping to the UCS clock, we see that the UCS or Unified Clock System is found on the F5XX and F6XX generation MSP430 devices. As we stated earlier, one of the nice things about the Unified Clock System is that it's orthogonal. By that we mean that any clock source can go to any one of the 3 internal MSP430 clocks. So this is the most flexible clock system to date. Also, as we said earlier, it has all the different clock oscillator sources that we discussed. So between the fact that it has all the different sources and they can go to any one of the 3 internal clocks, it's just an extremely flexible clock system on these devices. How do we use our clocks? Well, the primary thing is we need to select a clock source for each one of our MSP430 internal clocks. Luckily, we have driver library functions that help us with this. If you're working with the F5529, for example, you're going to use the UCS prefix for these functions. If you're working with the FR5969 FRAM devices, then you're going to use the CS prefix. Here's an example with the F5529. You can see that we just have a function, UCS clock signal init. So one function handles this for us. We can say which clock we want to configure. In this example, it's A clock. Which source we want to use. In this example, we're using the REF-O clock, that is the reference oscillator. And you might remember that there were some dividers. So along with selecting which clock source we wanted to use, there was a divider on that clock. The driver library function lets us program that divider, and you can see here we're just setting the clock divider to 1. Now, if you're going to use an external crystal as one of your clock oscillator sources, then there are actually 2 extra steps you need to take in order to use it. So once again, driver library will help us out with this. The first function we see there is actually a GPIO function. We studied those in the last chapter, but it's important here because the external clock pins on most MSP430 devices default to GPIO mode on reset. So we have to make sure we reconfigure those pins in their clock mode. The next function starts the crystal and waits until it's up and running before moving on to the clock signal init function. You might notice if you look down at the bullets at the bottom of the slide that there's a different LFXT1 start with timeout function. We actually have 2 functions in driver library that will start the crystal running. The one we show in our code, it's going to wait until the crystal is running. What happens if the crystal falls off the board or gets damaged in some way? In that case, it'll never start running, and we'll never leave that function. For some people, that might be good enough. If, on the other hand, you need a more robust solution, then use the one that's shown at the bottom. It has a third parameter that lets us specify how long to wait until we just time out and move on. If you use the with timeout function though, make sure you actually look at the result that's returned by that function. It's going to tell you if the crystal is running or not, and you'll probably need to take different actions in your code based on its result. To finish the clocking section, let's review by looking at this table. The first part of this table where it says available clock sources, well, we've kind of covered those details already, talking about which clock sources are available for each of the clocks, M clock, SM clock, and A clock, for the three devices we've been kind of examining. The value line device, the F5529 USB device, and the FR59 FRAM device. The next set of rows in the table talk about the clock defaults. So after a puck reset, what are the values of the different clocks? You can see that for the devices here, for M clock and SM clock, DCO is what gets set. So DCO, the 5529 has a signal based off of DCO called DCO clock div, and the FR59 uses DCO clock. And they're all in about the 1 megahertz range. A clock gets set to the low frequency external oscillator, whether it's named LFXT1, XT1 clock, or LFXT. It's basically the same clock source. Going down to the next row, external clock failsafe, it tells us what happens if an external clock fails. For example, on the F5529, if the XT1 clock, if the low frequency external clock fails, the Msp430 is going to automatically switch over and start using the reference oscillator. Similarly, if the high frequency external clock fails, then we're going to use the DCO internal oscillator. On the 5969, they actually use the mod clock as the failsafe. So for the low frequency external oscillator, it would be the LF mod clock signal, which is a divide down from mod clock itself, and that's the one that's used for the high frequency. Looking at the next row, DCO calibration, we see how each of the different families handles calibrating the digitally controlled oscillator. That is our high frequency internal clock. For the value line devices, a calibration constant is created during the test of the processor. That value is actually put into the info A memory, and you can use that constant during setup to get the best accuracy in your DCO clock. For the F5529, it's done differently. It actually has hardware, a frequency lock loop known as FLL, that actually calibrates the DCO at runtime, responding to various issues, whether it be voltage changing, temperature changing, or whatever. The FR5969 is actually different than either of the other two. It's factory trimmed. By that we mean they've picked a number of frequencies that are supported by the FR5969, so that over time and temperature you get the precision that they've described in the datasheet. The second last row just specifies whether you need a password in order to configure the clock settings or not. On the FR5969 devices, they've added that feature so that you can't accidentally change the clocking of the system. The last row is called clock request. What it basically asks is, can a peripheral keep a clock on? On the value line device, the only thing that we have is that you can't turn off the clock, which is supplying the watchdog timer. That's the only such feature it has. On the 5529 and FR5969 though, many of the peripherals have a clock request line. That means a line that goes from a peripheral to the clock. That way, if you try to put a device into low power mode, and that low power mode would turn off a clock that's needed by a peripheral, that peripheral can keep the clock from being turned off. Now, you don't have to use this feature, but it can be a handy failsafe. It can keep you from accidentally turning off a clock that was going to be used to wake you back up from your low power mode.